Hi Algebra 2, this is Unit 4, Lesson 7, and today we're going to talk some more about percents. So, as we talked about in the last lesson, exponential growth or decay uses the formula A equals P times 1 plus or minus R to the T. So I'm basically using that growth and decay formula all at once. If it's growth, I'm going to add the rate, and if it's decay, I'm going to subtract the rate. What we're going to do today is we're going to manipulate some of these percents in order to change the time scale. So like if I give you the rate for 1 year, we're going to figure out what that rate is over 5 years or 10 years. Or if I give you a 1 year rate, we're going to figure out a monthly rate. So that's basically what we're going to do. Percents can definitely be challenging because they're not linear. The growth is a multiplier. Okay, so to find the percent growth rate, I have this formula right here. The percent of change equals the difference over the original times 100. And we're going to look at that in this first problem that we're doing. A population of wombats is growing at a constant percent rate. If the population on January 1st is 1,027 and a year later it's 1,079, what is the percent growth rate? So I want to find the difference. So I'm going to take 1,079 and I'm going to subtract 1,027. And that gives me a increase of 52. Okay, so I take the difference goes on top, over the original. The original was 1,027, and I times it by 100. That whole thing goes into my calculator. All right, if you want to try it right now, you can pause the video and try it. I get 5.0632. Now I want that to the nearest tenth of a percent. So basically I'm going to say, oops, sorry about that. I'm going to say that it's 5.1%. 5.1%. Okay. And that is my percent. Now I'm going to continue on with that problem. Now let's try to determine what the percent growth in wombat population will be over a decade of time. So that was a yearly percent growth rate. Next one, I want a decade. So after 10 years, what will we have multiplied the original population by, rounded to the nearest hundredth? So I'm going to take that, I'm really just taking this part of the formula. All right, so I know that A equals the principal times 1 plus or minus the rate to the t power. I just want this part. I don't care about the initial population. I only care about the percent increase. I'm not trying to predict the actual population. So I'm just going to take this right here. So I'm going to take the 1, okay, plus, now my rate is 5.1%, so I need to change that to a decimal, so it's actually 0.051. I'm moving that decimal place over 2 places, and I want to find this over the course of 10 years. So 1 plus 0.051 is obviously just 1.051 to the 10th power. Okay, and that goes in my calculator. And when I do that, I get 1.64. All right. Now using that answer from part A, so that's my answer from part A, what is the decade percent growth rate? All right, and actually this is 1.644, like it kept on going on and on. So basically you are just going to forget about the 1. I'm looking at this part of my answer right here, but I want to change it back to a percent, so I'm going to move that decimal over 2 more places, back 2 places I should say, and it's 64.4% is that growth rate over the decade. Okay, because it's the 1 plus 0.644. So this is my rate right there, and I'm taking my decimal and moving it over 2 places. So that's all I'm doing to pick that apart. Okay, so you might have thought that if I have a 5.1 increase per year, that you really just have to times that by 10, right? My original yearly from exercise 1 is 5.1. 5.1 times 10 should be a 51% growth rate, but it is not 51% growth rate over the 10 years. It's 64.4%, because that is because you have percents on top of percents. All right, we're still looking at our wombats from exercise 1. Assuming their growth rate is constant over time, what is their monthly growth rate to the nearest tenth of a percent? All right, so I'm still going to take that 1.051, okay? So it's the 1 plus the growth rate, but that was for the year. If I want it to the month, then I'm going to do it to an exponent that is a fraction. So 1.01 to the 1/12th power is what I'm putting in my calculator. I'm trying to find the monthly growth rate, 1.051 to the 1/12th. And that gives me 1.00415, all right, which is 1 plus 0.00415. I take my decimal. This part right here is the rate that I'm looking at, and I'm going to move it back to percentages, to decimal points. So I have a 0.4% monthly growth rate. Okay, so keep in mind, to make a larger time period, you do an integer exponent. I'm going to write that down because it is important. To make a larger time period, like if I have a yearly and I'm trying to do 10 years or 5 years or whatever, I do an integer exponent. I'm not sure why my pen's not working right here. Oops. Let me move this up a little bit so I can write. Do an integer exponent. And to make a smaller time period, I'm going to do a fractional exponent. The next problem is a little bit trickier because I'm giving you a 5-year rate and I want a 2-year rate. So basically I'm going to take that 5-year rate and find out a yearly rate, and then I'm just going to do a 2-year rate. All right. So population was growing at a constant rate of 22% every 5 years. What is the percent growth rate over a 2-year span? All right. So this is my rate over 5 years, 22%. I can't just take that and divide by 5 and say that's my yearly rate. I'm going to, again, it's 1 plus the rate to the time period, right? So 1 plus 0.22. Now I'm going to make that 1.22, obviously. Now that's over a 5-year time period. I need to find the yearly time period. Okay, so let's find the yearly. So I'm going to take that 5-year and I'm going to make it 1 year. So if I'm making a smaller time period, my time is a fraction. So I'm going to do 1.22 to the 1/5. We'll convert that to a yearly multiplier. I need the yearly time. All right. So I can write down that yearly time. I don't necessarily have to write it down though. I then want to take that yearly time to calculate for 2 years. So 1.22 to the 1/5, but then I want that for 2 years. So I'm increasing it from 1 year to 2 year. I'm going to have an integer exponent. So I'm really just doing 1.22 to the 2/5, and that can go into my calculator. 1.22 to the 2/5. Okay. And when you do that in your calculator, you're getting 1.0827. Okay, everybody should know how to do that exponent in your calculator. It's right above the division symbol. It's that little up arrow. And if I'm doing 2/5, you'd have to do that and do 2 divided by 5. Okay, so this is what's going into your calculator, 1.22, that little up arrow to get the exponent, 2/5. And now, so this is really 1 plus 0.0827. And this part right here is my rate. All right, so then I'm going to take that and move my decimal back over. So I have 8.27%. Not too bad. All right, the next problem is different, so let's look at it quickly. World oil reserves, the amount of oil used in the ground, are depleting at a constant 2% per year. We would like to determine what the percent decline will be over the next 20 years based on this 2% decline. If I have a 2% decline, that really means I have 98% left. I'm depleting it by 2%, but I have 98% left, which is 0.98. I'm going to move that decimal over. I want to find out what it is after 20 years. So I'm going to take that 0.98, okay, and do it to the 20th power. 0.98 to the 20th power is 0.6676. Okay, you can pause this to try it in your calculator. That's the fraction of oil left after 20 years. The fraction of oil left after 20 years. But I really want to find the percent decline after 20 years. So if I have, and I'm just going to call it 66.8%, okay? I'm going to take this and I'm going to move it over 2 places. If I have 66.8% left, how much did I actually use? We'll subtract that from 100. 100 minus 66.8 is 33. I have, oops, sorry, I don't know why I keep on doing that. Let's get rid of that. So I really have a 33.2% decline. So that was a little bit different. I do want to try the problems on the next page because they have to do with half-life. So we'll try A and B. I'm trying to keep your videos as short as possible, but let's look at A and B. So a radioactive substance has a half-life. You've talked about half-life probably in science. Is the amount of time needed for half of the substance, 50% of it, to decay. Let's say we have a radioactive substance with a half-life of 20 years. What percentage of the substance would be radioactive after 40 years? The half-life is 20 years. I want to break that down into a 1-year period, so I'm going to raise that to the 1 over 20th power. And then I'm going to raise it to the 40th because I want to know how much is left after 40 years. So the 1 over 20 breaks it down to a yearly, and then I multiply it by 40 to figure out what it is over 40 years. Well, that's really just 1/2 to the 2nd power, because 1/20th times 40 is 2. And you could just do that in your calculator, is 0.25. So basically 25% of it is still radioactive. I wanted you to see the math behind it, even though you might have been able to do it without doing all that. What percentage of the substance would be radioactive after 10 years, rounded to the nearest 1/10 of a percent? Again, my half-life is 20 years, so I have to take it and break it down to a smaller yearly period. I do a fractional exponents 1/10. That's breaking it down to the yearly, but then I want to find it after 10 years. So 1/20th times 10 is actually just 1/2. In my calculator, 1/2, you can just put that in as 0.5, then use that up arrow to get the exponent, and I'm doing it to the 1/2 power. Again, 1/2 is just 0.5, and all of that gives me 0.7071. Okay, I got to move that decimal over 2 places, so basically 70.7% is still radioactive. Just because the half-life is 20 years, you're not going to say that you have 3/4 of it left after 10 years. That's not the way that it works. There is a formula down here on the bottom that I'm using for half-life. Okay, so that is right there, and we can use that tomorrow. That's exactly really what I was doing. I did 1/2, and then I did it to the 1/20th power because that was my half-life times the time. So they just took all of those exponents and they put them all together and